Good afternoon, everybody. Is that working? Microphone? Okay, thank you for having me today. I'm going to talk about concrete that uses rubber that's from recycled tyres. That is how many tyres reach the end of their life every year in Australia. So there's the Sydney Opera House. That's what the pile would look like if it was in Sydney Harbour. So over 56 million, and this is in Australia. In the world, it's about 1 billion tyres every year reach the end of their life. And unfortunately, only about 10% are recycled. Some of them, and in Australia, we then export some. Some of those are recycled, but many of those end up as waste. And there's still about 50% that we don't actually have any record of what happens to them. And mostly we know that they're just dumped illegally. So they'll just be dumped in landfills or dumped in old mines and all that kind of thing. So it's a massive problem. In Australia, there's an organisation that has been developed called the Tyre Stewardship Australia Fund. And for every tyre that is sold in Australia, there's now a levy, I think it's $1, that goes, so all the tyre manufacturers and retailers have signed up, and that money goes to Tyre Stewardship Australia, and they feed that money back into industry and research to try to develop solutions to use tyres. So there's a number of things that they can be used for and are being used for. One of them is road surfaces, so asphaltic concrete or bitumen surfaces. Playground surfaces, so just those bouncy kind of playground surfaces are old tyres. They can be used to reline brake pads. They can be used for industrial flooring. And then there are ways that you can change the chemistry, and they can be used as a component in explosives. You can develop a fuel from them, but at this point it's not necessarily economic enough. And then what we'll look at is some of the civil engineering applications that you can use them for. So you might wonder what crumb rubber concrete is. So concrete is just a mixture of water, some kind of binder, glue, which is usually cement, but it can be other things in cement, and then what we call aggregate, which is stone, sand, a mixture. In terms of alternative materials, cement is one of the worst greenhouse gas emission causes in the world. It's the worst, in fact. So a number of things are being trialled to change cement, to reduce the energy used to produce it, or to mix other materials, waste materials with the cement to change the binder. So you can do that kind of thing, and we do some research in that area as well. And the other option you have is that the aggregate, which is normally natural river sand and crushed rock or stone, you can replace some of those natural materials with recycled materials. So you can use crushed old concrete to replace some of the stone aggregate. And what we've looking at in crumb rubber concrete is that we replace some of the sand with crumbed rubber of a similar size to the sand materials. This one here is a cross section of a piece of concrete, and you can see those little black bits. They're some of the crumbed rubber pieces. Why do we want to do this? Obviously the scrap tyres is a huge environmental issue, but as well as that, natural sand that's suitable for concrete is also becoming more scarce and consequently becoming more expensive, mainly because it's getting sourced from further and further away, and therefore the transport costs are significant. If the tyres are dumped to landfill, then we end up with potential hazards of fires and breeding grounds for pests and so on. So the idea of crumb rubber concrete is we use a waste material and replace a natural material and get a more green solution. So when the tyres reach the end of their life, if they are recycled, they can be made into 3 kind of different sizes of materials. So the rubber chips, I don't think that's working anymore. Rubber chips would be what's used in the playground surfaces. Ground rubber is smaller, and crumb rubber is what we've used. It's a similar size to sand grains. But you can mix the pieces as well, and we've looked at that. The smaller that you make it, the more it costs, because there's more processing involved. This is just a picture of some of the kinds of tests that we've done with crumb rubber concrete. So they're all fairly basic tests that you need to do to understand whether this material can be used as a replacement for conventional concrete. So stress strain, creep, which is long-term deformation, looking at impact and so on. So I'll talk a bit more about some of those. The biggest problem with crumb rubber concrete is that putting rubber in decreases the compressive strength of the concrete. The more rubber that you put in, the more the concrete compressive strength decreases. So this graph is, not working. This graph is a mix. With no rubber, it was 62 megapascals, 5% rubber, 51, 10% 50, 20% rubber was 39. So you can see that it significantly decreases. We define the percent as the percent of sand by volume replaced by rubber. And although that's a fairly high compressive strength mix, the same pattern happens no matter what target strength you are aiming at. So the question is, why does it decrease in strength? And the main reason is that the bond between the rubber particles and the cement is not as good as the bond between sand and cement. And that's for 2 reasons, mostly to do with the surface of the rubber, the surface shape and impurities and things. And sometimes because the rubber takes up too much moisture as well. So lots of different ways have been looked at in terms of how can we treat the rubber to ensure that the surface is better for bonding to the cement. And some of the simplest ones is just wash it, so make it cleaner, try and get rid of impurities. You can soak it in different chemicals to try and, again, etch the surface. The problem with those is you soak it, then you've got to wash it to get rid of the chemical, otherwise the chemical will cause a reaction in the concrete. So you can do various things. You can pre-coat it with cement, and another one is that you can treat it by heating the rubber. And I'll show you that one. That one seems to be the most successful. But most of those don't actually make enough difference to make it worth doing. You may as well just accept that it loses strength. We'll work around that. So hopefully you can see this, it's clear enough. So this is an electron microscope view of the rubber in the concrete. So this one here is untreated rubber. So the red pieces, the red arrow pieces, they're pieces of rubber. The yellow pieces turn out to be, if you think about a tyre, you have rubber, but you also have steel and cords that are in the tyre and so on. And even though they try to remove those when they recycle it, they don't succeed in removing it all. So all these yellow arrow bits are little pieces of impurities that are still stuck to the surface of the rubber. And this one is a closer scale. So you can see that little piece there, for example, or that piece there, and this is the main piece of rubber. So those are the things that are stopping the bond from happening. This picture here is of rubber after it has been put in an oven at 200 degrees. And basically you can see that all those little pieces have disappeared. If you look at this one, so what you now have is a rubber surface that is clean and also a bit rougher, so it's going to be better for the bond. What we have to balance out is, you know, the cost of heating the rubber and whether that makes it worthwhile or not. So this is again a graph of compressive strength. This one here is no rubber. So that one's just over 50 megapascals. The blue is untreated rubber and the red is the heated rubber. So you can see that heating it, we still lose some compressive strength, but we don't lose anywhere near as much. So that's looking promising, except that when you do it, it stinks your lab out. So it's, you've got to be careful with the extraction fans. One of the other things that crumb rubber concrete has is very good impact resistance, which is probably not surprising. So there are, although the compressive strength decreases, there are other things that are significantly better with rubber concrete than they are with conventional concrete. So we've got to try and use the good things and work around the bad things. So what can you use it for? You can basically use it for anything that you use conventional concrete, but we still got to do the last kind of set of tests to really be able to kind of take that out to the market. So this is looking at, again, not surprisingly, it's good in earthquake environments. It has, as we said, it has good impact resistance, it has good energy absorption. So this is comparing conventional columns in earthquake situations with crumb rubber concrete columns. They've all got fibre reinforced polymer wrapping around them. This is another application of columns where these are segments that have a hole in them and you have a rod through them and then you tighten up the rod. So that's a post-tensioned column. Based actually on ancient Greek columns, which are all separate segments. And that works very well in earthquake situations. And the crumb rubber didn't have any kind of disadvantage at all. So it was another good use. It can be used in beams and beam columns. I mentioned that it loses compressive strength. But if we look at a beam, just curious, are there any structural engineers in the room? Yes? No? Okay. All right, I'll explain. We'll put that down. Okay, when you bend a beam like that, the top is compression, the bottom is tension. With a beam that looks like that, it's what we call ductile, and the compression zone, the piece at the top, out of that much, the compression is only this much. The rest of the beam is in tension, the concrete doesn't do anything, and you rely on the steel. So what that means in a beam is that the compression is not a very important part of the structural behaviour. So if the compression strength is a bit less, it doesn't make much difference. But what is good about rubber concrete is it improves the cracking behaviour. So the biggest problem with a beam like that is you'll get a big crack here and a few more big cracks near there. But with rubber, the cracks are smaller and there's kind of more of them spaced out and much smaller. So it ends up being a better beam, stronger beam, and more ductile. It can bend more, which is good. That's just another application of wrapping existing beams with new concrete. We've also looked at it in lightweight concrete beams. And again, the compressive strength is not a disadvantage and they perform basically as well as conventional beams, but they also have better deformation properties. We're also looking at suspended slabs, so first floor slabs. These ones are the ones that are on steel formwork that acts as formwork and reinforcement. Very common for all suspended slabs. So we're looking at how does the concrete stick to the steel? Is there any difference with the rubber concrete compared to conventional concrete? Again, so far, no problems. And this is one of those same slabs undergoing bending. And again, so far, the performance is better because again, compression zone is very small, ductility is better. So the main focus of our current research program excuse me, is looking at crumb rubber concrete in residential, so housing applications. And that's because Tyre Stewardship, who have funded this research, they want to use lots of rubber. So they are looking for applications that can use a lot of the volume of tyres that are generated. And concrete in housing accounts for about 40% of all concrete made in Australia, and that would be similar in other countries. And if you do the numbers, the actual volume of rubber that you could use if we replaced 20% of the sand with rubber, the actual volume we could use a significant number of tyres. So something like about 50% of those being generated, just because there's so much volume of this concrete being used. And the good thing is, for housing, it doesn't need to be high strength. So the disadvantage that crumb rubber has isn't that important in housing. Paving is also another application that we're looking at, so footpaths and road pavements. There is a slight cost penalty of the rubber compared to the sand at the moment. That's getting closer all the time. So it would still be a premium, maybe about a 10% premium. So it would have to be marketed as a green material, you know, environmentally friendly material, etc. But that price gap is closing all the time. So this research project is a 3-year project that we're most of the way through. We started out by developing new, optimising the mix of concrete, how much water, how much binder, all that kind of thing. Then we've started and we're still looking at the durability and the long-term behaviour, because that's going to be probably the make or break for this material. If you can get it to work from a strength point of view, but it doesn't last, you know, that water can get in more easily, or the reinforcement rusts or whatever, then it'll be a problem. So we're still doing those tests. As you could imagine, they take a bit longer to do. Even though we have accelerated tests, they still take a while to do. But so far it looks good. So far there's no problems with that either. The bond, so how it sticks between the steel reinforcement and the concrete, is another key thing. Again, that all looks good. And we're looking at the slabs, you saw some of those. And then the main thing that we will have to deal with is convincing the construction industry that this material is something that they can use. So as you all know, construction is a very conservative industry. So we're talking about a fairly significant change to a material that they've used for ages. So we will have to convince them. And the problem that we have is, as researchers, all of this work is done in the lab, and you're using little mixers and little cylinders, and how does that translate to a big batching plant, and it's going in a truck to the site, and what happens then and whatever. So that's what we've been focusing on now. And we've poured a couple of large-scale slabs in conjunction with a concrete mixing company. And we did find that what we thought was working in the lab didn't work. The first batch that we got, you could hardly get it out of the truck. It had, you know, one of the things with concrete is it needs to be runny so that they can smooth it and all that kind of thing. And this concrete was almost like a rock to start with. And all it was they mixed it in the wrong order. So they put the rubber in, they put some water in, then they put the rubber in, and the rubber just went, took all the water, and so the mix was really stiff. We just changed the order. We had actually changed the order, they just didn't listen to us about changing the order. And then it was fine. So we got some footing contractors from industry. They've given us feedback. They said it was easy to work and so on. And we're going to monitor these slabs over the following 12 months. So we poured them about 2 months ago now, which is really, I really like this because it's really practical. So I'm calling this from the lab to the slab. So this is where we're up to at the moment. What we've found so far, as I said, is we've worked out some good mixes. There are differences between laboratory versus a batching plant, but we've sorted those. And so far, everything's going well, and it all looks promising. So we've got about another 18 months to go. These are the other people who are involved in this project. And these are the industry partners that we have associated with the project. So we've got the funding body, a consulting engineering company, the concrete company that looks at recycled materials, the tyre processing company, and a cement and concrete kind of consultancy expert. That's it. Thank you.